Welcome to our last unit in AP Physics B on modern physics. Now, everything we've studied up until this point in the course has been known since the late 1800s. We've learned about Newtonian mechanics in the first semester and thermodynamics, and then recently we've been studying optics, electromagnetism, and this era of physics is known as classical physics. The physics before 1900 was known as classical physics. Many scientists of the late 1800s believed they had learned basically all the physics theories, and they could just about explain everything. However, things change when you find new experiments that don't agree with the current theory. So we soon started to realize in the early 1900s that our classical laws of physics were limited. For example, Newtonian laws fail to explain why when objects move near the speed of light, our laws of physics don't work. You get things like length contraction and time dilation. It's not that the theory is wrong, it's just limited. It only works in a certain range. And we end up with a field called Einstein's theory of relativity, which explains the physics of objects traveling at super fast velocities near the speed of light. In a similar way, quantum mechanics works in explaining the physics of tiny objects. So, by the late 1800s, this brings us to the end of the era of classical physics. At about 1900, several experiments were done that led scientists to believe that light behaves as a particle rather than just being only a wave. Suddenly, physicists could not explain the structure of atoms. They could not explain the atomic spectra, or black body radiation, or the origin of X-rays or radioactivity. Experiments like the photoelectric effect could not be explained by classical wave theory. So it soon realized that light and matter exhibit characteristics that are both particle-like and wave-like. And Niels Bohr set forth a principle of complementarity, which stated that either wave theory or particle theory, but not both, could be used to explain light and as well matter. So what do you need to know about wave-particle duality? Well, you need to know that light sometimes behaves as a particle and sometimes behaves as a wave. You should know the following experimental evidence that shows that light behaves as a wave. For example, the interference of light. We studied in the previous chapter Young's double slit experiment. That's evidence of light behaving as a wave. Also diffraction, refraction, and polarization. All of these are evidence that light behaves as a wave and can only really be explained by wave theory. Then we also have, which we'll be studying in this unit, experimental evidence where light behaves as a particle. We have black body radiation, which we'll be discussing after this video. We have photoelectric effect, which we'll also discuss later on. Compton scattering or Compton effect, and the atomic spectra. Maybe you've seen that in chemistry, where you've seen the gas discharge tubes. That can be only explained by particle theory. Furthermore, in classical physics, we assume that matter consists of small, indivisible particles. We think of atoms and electrons as tiny particles, but we'll discuss later in this chapter a French physicist by the name of Louis de Broglie, who reasoned that if light can be perceived as both a wave and a particle, then couldn't we also say that matter behaves as both particles and wave-like as well? So, you'll see later on that electrons and protons can be thought of as waves. So you could think of an electron has an associated wavelength. And just after de Broglie made this hypothesis, it was experimentally verified by the Davidson-Germer experiment involving electron diffraction, which showed that matter behaves as waves. So I should also point out that there is experimental evidence of matter behaving like a wave, and that would be the Davidson-Germer experiment that you'll see later in these chapter notes. And lastly, you may have noticed when we talked about the electromagnetic spectrum, You may notice that the waves, we have infrared waves and microwaves and radio waves. And so physicists who tend to work at this end of the spectrum tend to observe the wave-like nature of the EM waves here. However, over here to the right side, where we have ultraviolet rays and X-rays and gamma rays, you can think now as these EM waves being more particle-like. So let's dive in and study the modern physics era.